Hey there, are you set for another quick lesson? So here comes your Unit 9. This is going to be very theoretical, but yet we've seen most of the theory in this section, so it should be fairly easy. It should be more like a review. So this is about collision theory. So first, there are two types of collisions, illustrated here. So we have elastic collisions, and we have inelastic collisions. Now, as you see in the drawing, elastic collisions basically doesn't yield a reaction. So your particles are just going to bump into each other, but they're going to go back in different directions unchanged. In order to have an actual change, an actual reaction, you need an inelastic reaction. That will then create an actual chemical reaction and will create products. So now, what do you need to have an inelastic reaction? You need two things. You need the right orientation, so your particles have to collide with the right orientation. You can think of a car accident. If you have a frontal collision, it does much more damage. So it's the same thing with your particles. If they collide with the right angle, there's a better chance that they will break apart and will be able to kind of reconnect after and to form different products or different substances. So that's point number one. And point number two, they need to collide with sufficient energy. If the collision is very slow and doesn't involve much kinetic energy, well, the chances are that those molecules are not going to break. So you need high energy and you need the right angle. When both those factors are present, then your particles, your molecules can break apart and can create new substances, so you can have an actual reaction. So when we compare the amount of elastic collisions and inelastic collisions within a certain amount of time, if you have more elastic collisions, so I have more of these and less of these, I'm going to have a very slow reaction because most of these collisions are inefficient. Now, if I have the reverse, if I have a very small amount of elastic collisions, but I have a larger amount of inelastic collisions, so efficient collisions, then I'm going to have a fast reaction because most of the collisions are being efficient and are yielding a transformation. Okay, so what is it that really happens during a reaction? We've seen a standard graph with the activation energy over here. So we know that the particles have to kind of go over this hill. So they need to have sufficient energy to reach the activated complex where all the particles are separated, and then they can go down the next hill in order to make the product. So what's really happening in that is that these reactants here are colliding with each other. So some particles have elastic collisions, nothing's happening. So it's as if it's a roller coaster that goes up the hill but doesn't go fast enough up the hill and comes right back down. But some of them collide with the right angle and sufficient energy, and that allows them to reach the top here. So that means that the particles are basically separating and that we end up with single particles that are ready to reconnect together in order to become the products. And we know that during those processes, there's energy that is gained at this level, which is similar to the activation energy, except that this is the first jolt of energy that needs to be given to the reactants, as opposed to this here, the bond's broken. Well, this is ongoing during the reaction. So this is really the primary energy, the activation energy. It's the primary energy that's given at the beginning of the reaction. So you have to make the distinction between this and the ongoing energy that has to be supplied to the reactants in order to break their bonds. And then once we reach the activated complex, there's some energy that's released during the formation of the bonds to create these products over here. So that's really what's happening during a reaction. We've discussed that already, so this should be review for you. Next. Now we have the Maxwell-Boltzmann distribution energy diagrams. So basically the way this works, let me just scroll down a bit because I think it's easier for you to understand it this way. So we're looking at the amount of particles, they say molecules could be single particles as well, versus their speed. So some particles, let's say in this case four particles have a lower speed, 6 particles have a slightly higher speed, 16 particles go at 1,000 meters per second. We have, let's say, 13 particles that go at 2,000 meters per second, 10 particles that go at 3,000 meter per second, so on and so forth. So we know that the faster they go, the more likely they will actually collide, break apart, and basically react. So what we're doing here is that we're determining at what energy or what speed, because we can basically translate speed into energy. They're kind of equivalent because we know that the kinetic energy is equal to 1/2 mv for velocity squared. So the energy, kinetic energy, is directly related to the speed of the particles. So the higher the speed, the higher the energy they have, and the higher the energy, the more likely they will react. So these over here, let's say, are more likely to react than these over here. So we could say, for example, that this threshold, this barrier, energy barrier here, is basically the equivalent of the activation energy. So if you look at a graph like this, the way it's distributed, if you look at the curve, they basically drew a curve on top of the bars that you had. So you have that over here, something similar, and they did show the activation energy, and they said, well, you know, all these particles here that have more speed or more energy are more likely to react. So these particles have sufficient energy to react. They have more energy than the activation energy, than the energy required to go over the hill. Now these here don't have enough energy, so they'll have elastic collisions, as opposed to these that will have inelastic collisions. So that's the way that these graphs work. It's just a distribution of particles. So how many particles you have, let's say 11 in this example here, 12 over here, for example, versus their speed or energy, in other words. Finally, when we look at a reaction mechanism, if you remember, a reaction mechanism is something that has several steps. So there's more than one reaction occurring. It's a series of reaction that creates a whole bigger reaction called a mechanism. So sometimes we compare that to a chain, like when we build cars, there's different people doing different tasks, and all together they create a car. So it's like an assembly line, basically. Well, if this guy, for example, is working super fast, well, the cars, it's great, they're gonna, go further, but further up the road over here, there's another person that, for whatever reason, maybe their task is more complicated, their speed is slow. So the speed is low or slow. So that means this guy can work as hard and as fast as he likes, but that's not going to change anything because the person in front over here is slowing down the whole line. So who's really deciding on the speed of the whole task or of the whole assembly line? It's the slowest person. So it works the same way for a chemical reaction. So if we look at the graph over here, we have 4 different parts to this assembly line or to this reaction. So which one would basically decide the speed of the mechanism of the whole reaction? Well, it will be the one that is most difficult to kind of go through. And which one would that be? Some of you may say, well, it's this one because it has a very large activation energy. In a sense, you do make sense. You're not quite entirely wrong, but there's something more difficult than that. It's actually this one here because the peak is even higher energy-wise. So this activated complex is so high that it's even more difficult to attain, even if it's slightly shorter than this one over here. So it's like saying, I have to go from a certain street downtown in Montreal and go towards the top of Mount Royal. Yeah, it may be a hike, but what's even worse is having to climb from the top of Mount Royal, going down into the valley and having to climb another mountain that's even higher. There's less oxygen up there and it's tougher to climb, it's more rocky, and whichever way you want to put it. But basically, because the energy of the activated complex is the highest over here, that's the highest value, this is what we call the rate determining step, so the one that will determine the speed of the whole mechanism. So always look at the highest activated complex. That step will be called the rate determining. Actually, why am I writing that here? Rate determining step over here. Okay, so step 3, rate determining step. There you go. That's it for chapter number 9. See you for chapter number 10.